Okay, Rick McCulloh holds a BS degree in geology from Oklahoma State University and a master's in geology from University of Texas at Austin. He joined the Louisiana Geological Survey in Baton Rouge after working for 2 years as a geologist for Conoco Minerals in the Texas Uranium District. At LGS, he's been involved in mapping and compilation of surface geology at scales ranging from 1 to 24,000 to 1 to 500,000, as well as other surface and subsurface investigations, including stratigraphic configurations associated with Miocene growth faults, delineation of shale field channels in Wilcox Group, surface and shallow subsurface geology for emergent salt domes in coastal Louisiana, and structural geomorphology as reflected in stream nets and alluvial courses. So we're happy to have Rick here to present on the surface geology of Louisiana.
Yeah, that works. It's just maybe not close enough. How about no? How about that? No. All right. Let's just go with the. How about that? Okay. Thank you, Chris. And thank you, NOGS, for inviting me to be here. I'm guessing that some of you here today have probably had an experience something like the following. You're looking at a map of surface geology, and something catches your eye, and you think, I think I'd like to go out and see that on the ground. And the weekend comes, you make a day trip, and when the day has ended, you've at least had a nice change of scene, but you may be wondering more than ever, how did they map that, and why did they map it the way that they did? What I hope to do here today is to summarize for you what the Louisiana Geological Survey approach to surface mapping has been for about the last 2.5 decades. The opening image here, view of the LSU campus. It's got two basic landscape types. There's an upland landscape, which corresponds to the oldest map unit in the view, and a bottomland landscape, which has all the younger units. That is a theme that we will return to. Oops. Wait a minute. Page up and page down? Arrows are not working. How about this? Just do it like that. There you go. Well, that's strange.
Yeah, it's like it's locked up.
Well, I'll continue talking.
Yeah. There we go.
Basically, I was going to start by drawing a contrast between our situation, which is coastal plain, humid subtropical.
The arrow keys are working.
Okay, great. Thank you, Chris. If we just go one state over, it's a big state, but we have a semi-arid situation here, and we've got old rocks. They're older than Cenozoic, at least, and they're hard. Even though they're limestone, they're harder than what we're used to seeing here. And so this is an area with essentially no cover to speak of, no cover at all. And as a result, you can just look at a view like this, and you can see at a glance that we have a dip slope surface on the top of the limestone unit. It is displaced by intersecting faults, and in between the faults you can see intersecting joints parallel to those faults. And you can see all of that just because there's nothing to hide it. In the coastal plain regions, which in this rendering includes our entire state. We have young strata, and we also have a humid subtropical climate. In fact, in some classifications, humid subtropical corresponds almost exactly to that coastal plain rendering that you see here. So as a result, if you have a field project in Louisiana, you drive to your field area, step out of the vehicle, this is what's facing you more often than not. There's lots of vegetation, lots of cover, and the exposures that you do have, sometimes they're not permanent. Well, you could fix that, I guess, with subsurface data, but it's a little more complicated than that because, for one thing, we have two sets of data. There's a shallow data set and a deep data set. And the two don't really overlap each other much because the shallow wells average, let's say, a few hundred feet, and the deep wells, the records of the information record doesn't begin until a few thousand feet down because of the surface casing. Now, there are places where they touch each other, overlap a little bit, so you can do things in some places, but as a rule, it's complicated. This is a cartoon just to illustrate what I was describing. Land access. I can't back this up with any numbers or data. This is just my impression of reality and how reality has changed since I was a kid. I think the world has gotten more fragmented, and I also think that the developmental footprint has gotten denser. That's true pretty much across the country unless you're talking about federal lands out west that you might have an opportunity to work on, perhaps. In Louisiana, most properties, if you just are going out and you haven't made any kind of advanced contact with somebody that you know to be the landowner, you're going to find most places are gated and posted, and the two largest controllers appear to be timber companies and hunting clubs. So in spite of all these difficulties, we have actually managed to make some steady progress in the last 25 years or so. This is owing entirely, almost entirely, to federally funded support projects. There was a program called COGIA-MAP back in the late 1980s to early 90s, and then that got succeeded by what they call the State MAP program in 1993. The COGIA-MAP program emphasized 1 to 250,000 scale mapping. So it's 1 by 2 degree quadrangles. State MAP emphasized 30 by 60 minute and also 7.5 minute. So it's much larger scale. And because of this assistance, we've managed to complete 1 to 100,000 scale coverage of the state in at least draft form. The yellow tiles there are finished lithographs. The blue ones are, right now, they're just GIS data sets. The State MAP program was actually part of the National Cooperative Geologic Mapping Program. It was set up by Congress, and it's renewed every several years, and it's administered by the U.S. Geological Survey. And the State MAP component has the specific objective of supporting new geologic mapping in the states. And the prioritization can be geologic or socioeconomic or both. Socioeconomic is an important thing to make use of, I would say, based on experience. Why was the National Cooperative Geologic Mapping Program necessary in the first place? This is what I would say. If you go back several decades, there was a lot of geologic mapping being done, and a lot of it was being done in academia. And somewhere in the decade of the 60s, I think, the diversification of geologic research techniques expanded the field so much that geologic mapping, by comparison, became smaller. And it may have actually suffered, it may have actually fallen out of favor to a considerable extent. So the Association of American State Geologists got concerned about this trend. And in the early 90s, they lobbied Congress. And I don't know exactly how they did what they did, but they actually managed to pull it off. And so we have these contracts now on an annual cycle, which is kind of a good news, bad news thing, because the good news is you can complete a project in a year. The bad news is you only have a year to complete a project. And some of these places really need more time than that, but that's kind of how it is, and we have to adapt to that. And I think something that is applicable in Louisiana is that since the early 20th century, probably the interest in deep subsurface oil and gas has essentially eclipsed too much interest in the surface. Well, with the problems of cover and things like that, are there things that we could use, techniques we could use to help us do our interpretations? And this comes back to the first slide where we had the two landscapes. This is a diagram originally from Harold Fisk, and it's slightly modified in places. It's simplified to show two depositional cycles. And he's got depocenters loading the crust at the edge of the continent, setting up a hinge situation. And as a result of that, up dip of the hinge, the older sequence is relatively uplifted relative to the younger sequence. The younger sequence has incised the older sequence. And so these would be like two different map units in the analogy that I'm drawing here. And I put Baton Rouge and New Orleans on here. That's just kind of schematic, but the red layer would correspond to Fisk's Prairie Formation, Prairie Terrace, and the yellow sequence would correspond to Holocene alluvium, Quaternary alluvium. Oh, and if we were to make a strike section about where it says erosion or Baton Rouge, that area, it would look something like this. This is an actual cross section, but it has about the same level of simplicity or complexity as the schematic diagram that Fisk made. The orange is the oldest, yellow is the next youngest, and the gray is the youngest. And you can see that each one is cutting into the next, and the younger you are, the lower you lie in the landscape. And so that's a very useful thing to be aware of and to key on. If your study area is big enough, though, you get a lot more than 2 of these sequences, and it can get complicated. And this is where some detailed criteria for characterizing landscapes can come in very handy. And the principal ones that we key on are the elevation range, the slope, the degree of dissection, and relief. And you can do this in small drainage basins. The Little River Drainage Basin occupies an area in north central Louisiana. And you can see here we're going from Jackson Group, Eocene, into the Pleistocene, and then we get younger and younger Pleistocene, and finally we're in Alluvium. We're stepping down every time we change units. And that's the youngest of those Pleistocene units when we actually encountered it in the field. So our basic strategy is to start by creating new mapping of Pliocene and Quaternary units using the best elevation data that we can get our hands on. I don't know how many of you are aware, but Louisiana did not have 7.5 minute coverage anywhere near complete until sometime in the early 1980s. If you look at an index map dated 1975, only about half the state is covered by 7.5 minute quadrangles. And then in the 80s, what happened was the USGS just released a flood of provisional quadrangles, which was a great thing because you had the information, it just wasn't finished cartography. So that was a great thing. Going from 15 minute to 7.5, big increase in resolution. And then now, of course, we have LiDAR, which is a big increase over the 7.5. So with that, we can delineate the Pliocene and Quaternary units. We integrate that. If we have tertiary in our area, we integrate those two together. The tertiary was, most of it was mapped back in the 30s and 40s, and it's actually still quite valuable because much of the state was clear-cut back then. And you could actually go out and see things that you can't see today. So we integrate those two together, do some strategic field work, and then recompile. Sources. Traditionally, aerial photography and topographic base maps. I personally haven't found aerial photography to be really helpful in Louisiana because I just can't see through the land use. And even with stereo pairs, it can be very difficult. Radar I've only seen in 1 to 250,000 format. If it was available in something larger than that, I would like to use it because it sees through clouds. Basically what I use the most is topography, 7.5 minute topography, and LiDAR. I use the NRCS soils data for reference whenever I'm head scratching about something. And then, of course, the legacy mapping of surface geology that has our tertiary units. What about faults? This is an excerpt from a tope sheet in the Baton Rouge East Quad. And you can see, I think, running from the left, kind of east-southeast to the right, there's about 3 contours piling up there. It's possible in Pleistocene terrain to make a decent map of these faults because they make distinctive landforms, they're active, and they're displacing Pleistocene surfaces. So there's an example of that kind of mapping, and then there's the LiDAR. The thing the LiDAR does that is really helpful is it shows things that you would never do if you're working with contours, because you're in smoothing mode whenever you're working with contours. So I'm going to have to actually point at this. You get these sharp pointed cusps like this. There's another one down here. And these appear to be places, shout out to Nancy, fault linkage. Places where formerly separate and echelon segments linked up to make a single fault trace. So this whole South Louisiana is in flux right now because LiDAR data is free. It's available to everybody. Anybody who wants to play with it can do so. And it's changing rapidly. And I expect that with the NOGS Fault Atlas, that southeastern Louisiana will change a whole lot more. So here's an example of a finished 30 by 60 minute quadrangle. It was manually compiled in the mid-90s, pre-LiDAR. And so the faults on it are also pre-LiDAR. The main thing that I'm interested in calling your attention to here is all those wetlands. How do you do geologic mapping in wetlands? Well, actually, you have to have drilling. But fortunately for us, the Army Corps of Engineers has spent several decades doing drilling in the Big Bottomlands and the Delta Plain. And they have put out a whole series of Atlas format technical reports. If you're not familiar with them, the hard copies are probably kind of hard to come by now, I'm thinking, but you can download it all. You can download scans from the Army Corps website under coastal plain mapping, I think. So that is a great thing. That framework that the Corps provided based on drilling is a really great thing. Where we can improve on it is by using depositional topography, because Holocene, the facies are our map units, and the facies are associated with particular geomorphic expression. So as I was saying a minute ago, if we go from 15-minute to 7.5-minute and then to LiDAR, we've made a huge jump in resolution, and we can always improve on the mapping. So just to review, the natural levees sit the highest, the interdistributary sits the lowest, or if you're in the alluvial plain, it would be the back swamp. And the intermediate elevations are the meander belts and the crevasse plays. So this is a project area from 2009. This is a view of that portion of the state geologic map with some annotations. We did the New Orleans and the Terrebonne Bay 30 by 60 minute sheets. This is a mosaic of the Corps' mapping in 15-minute quad format. And I'm going to zero in on the northeast, which is the New Orleans quad, 15-minute quad. There it is. And you can see the abandoned courses in yellow and point bar sand in orange. And this is a LiDAR mosaic of the same area. I want to call your attention to the elevation shading on the left. It's set up so that all the elevations below sea level are in shades of purple. Sea level is kind of a chalk yellow color, and all the other colors are above sea level. And one thing you probably notice, I think, is that the areas below sea level are all bounded by cultural features, roads, canals, and levees. And this is a function of development in wetland soils, which is useful to know. I mean, it has no geologic significance particularly. Zeroing in on the southeast corner of that area, this is Bergenville's 7.5 minute quad with the DRG, the topo sheet information combined. And you can see some branching coming off of the natural levee of the Plaquemine Delta complex. And profiled it just because some of the branches are below sea level, some of them are mostly above sea level, so wondering, you know, should they be matched differently? But the profile shows that the relief is comparable. So here's how we mapped it. The red lines are draft contacts. The yellow line here is the boundary between the St. Bernard and Plaquemine Delta complexes. And this is a view of the entire project area with draft contacts. In the delta plane, all we had was Kuchar's dissertation, essentially. And it's all Holocene, so there are no landforms. And but Kuchar did his research using geophysical techniques. He had shallow seismic, surface conductivity measurements, and cone penetrometer profiles. So this is the draft New Orleans 30 by 60 minute quad delivered to the USGS. And this is the finalized lithograph. And now I'm going to just run through a few other study areas. This is fiscal year 2010, Morgan City and Atchafalaya Bay. Morgan City is kind of neat because it has all the 5 islands in its extent. And there's the Morgan City lithograph. Monroe North, up at the state line with Arkansas. And there's the Monroe North lithograph. And Natchitoches. So having finished, in draft form at least, all the 30 by 60 minute quads at 1 to 100,000 scale, now we are returning to 7.5 minute mapping. For a while we were trying to do both. We were trying to, we would propose a single 30 by 60 minute quad, and we would do like 2 or 3 7.5 minutes in that area. But at some point our advisory committee felt like, let's just get the 30 by 60s knocked out as best we can. So that's what we did. We quit doing 7.5 minute mapping for about 5 years or so, and now we're going back to that. The purple tiles are areas that the committee has given priority to. The kind of beige or tan colored tiles are completed, and the kind of pale green ones, 2 areas in South Louisiana, those are the ones we're working on in fiscal year 2017. This is one of our earlier efforts. It's the eastern portion of Sicily Island, if you're familiar with that, up in North Louisiana. And this is one of the ones we just delivered less than a month ago for fiscal year 2016. I want to say something about mapping alluvium, which I know it probably doesn't get anybody too excited, but the problem is it has to be done. And we have a lot of it, and its contacts can get very complicated. And so you really have to take the opposite perspective than you would if you were in a hard rock terrain or something, where you basically map everything that you can as a map unit other than alluvium. And then anything that's left over that's down in the stream valley, you can call it alluvium. You could do that. But here, like I said, there's a lot of it, and it's complicated, and it's a grueling task, but it'll bite you if you don't get ahead of it. So yeah, it's minor volume, minor significance as a unit. I say it has indirect significance in places. We'll look at that in a minute. And the other thing is, if you don't take it seriously, your map is going to show that, and that might reflect poorly on other aspects of the map. So anyway, this is 10 quads in Fort Polk area. We're going to come down to one of them, Simpson South. Just looking at this colored view, it doesn't really look like the alluvium is that much of the area. But if I just look at an uncolored tracing, it gives a different impression, especially when I look at everything that's not alluvium. So I was wondering how much is actually on that quad, and according to the GIS, it's about 29%. That's still substantial. It's about almost 30% of the area. This is part of a 30 by 60 minute deliverable from 25 years ago. And there's an upland area on the east and the Mississippi floodplain on the west. And I think you can see that the way the alluvium is rendered, it's kind of crude. Now, the actual non-alluvial contacts in the uplands on this map are very pioneering, I would say. They did a lot of the heavy lifting. They're just not mapped with great precision. But the point is that this is the map that actually broke the ground, so to speak, for the edition that followed, which is this. But this has a more realistic looking depiction of the alluvium. But the non-alluvial contacts in the uplands are essentially the same as those from the 1992 edition. Indirect significance of alluvial valleys. If I see rectilinear patterns of alluvial valleys, it always gets my attention, especially when we have the Tepetate fault system here, and they're not paying any attention to each other. This is going to be the subject of my talk in a couple of weeks in Baton Rouge. You can see Bayou Serpent, which is aptly named, and the Calcasieu River Valley appears to have some straightness and parallelism with the northeast trending courses of Bayou Serpent. And one thing that I've learned doing this kind of mapping in Louisiana is that you never know where you're going to run into this, but you could potentially run into it anywhere. As long as you're not in the middle of the Mississippi floodplain or Delta plain, you could see this anywhere. And It's kind of like Geology 101, rectangular drainage, except I would not use rectangular because it requires 90-degree junctures. So, and we have all angles represented. This is a continuing dynamic. Every time there's a new large-scale map prepared somewhere, it becomes available for incorporation into the next synthesis at an intermediate or a smaller scale. And every time there's a new intermediate scale map, it stimulates interest in individual small areas. And so the two feed back to each other. That's it. Yes.
When you say alluvium, you really mean Holocene, right?
Yes.
All right. I would think that that would be pretty important because that would tell me where it is geologically reasonable to assume there could have been another flood. Thank you very much for selling me that lot for about $200,000 retirement home.
Nancy.
The statewide LiDAR was kind of a game changer.
Yes.
So I'm wondering if you guys have some sort of rule of thumb where, how far south into the coastal zone do you find it useful? Because I know that there's a point at which, once it becomes too wet, too marshy, you just don't really get neighbor resolution.
Well, I hadn't really thought of that. I'm sorry. I hadn't really thought about that. I guess I'm more of a high and dry upland kind of guy, and Paul's the one with more webbing between his toes. My perception is I don't see any latitude where LiDAR becomes unuseful to me. That's just my feeling about it. And Paul makes very good use of LiDAR in some very marshy situations. I think Chris was telling me about one example before the talk here. So I don't know. I probably can't give you a good differentiated answer to your question. Yes.
I noticed you weren't putting in formation names. Back like 40, 50 years ago, we had the Prairie Formation. We had some of those, and always had a problem naming a formation on the erosional surface that, that cuts it. Are you using formation names at all in the south half of Louisiana?
Yeah, actually, we use this allo stratigraphy.
Okay.
That's just, the ranks are all the same. Allo group, allo formation,
right.
Allo member. We don't get into members really, but the only thing that allo stratigraphy does is, and some people really react violently against it. I didn't realize this, but Paul and I had a reviewer number 3 on one paper who just, it's like his head exploded or something. But it's nothing magic, it's nothing highfalutin, but it does, it's like it was tailor-made for these lenticular units like we saw on Woody Gagliano's cross-section. It's tailor-made for that. And so if I can say that something is an allo formation, that's just a tip-off to a user that that's the nature of that unit. But yeah, it's prairie formation. Today we're using prairie as a group, prairie allo group. Yes?
Are these maps available to the general public?
Yes, they are. And many of them are available for free download in PDF format from our website. Yes?
Is there a GIS clearinghouse for the data?
Not yet. That's kind of a we're lagging in that department. We have a guy now who's working on getting metadata prepared for all. It should have been done previously, but it has not been. So we have not released the data except to individual inquirers. But if you have something you'd like to have access to, just send me a note and we'll see what we can do.
Great. Thank you very much. Excellent talk. And I hope this is the beginning of a future of real engagement between survey and NOGS. We can close that gap between the surface and the subsurface. Thank you all very much.